Okay, well, first of all, I would like to thank the organizers for this opportunity, and I would like to wish everybody safety to them and their loved ones. So today's talk is about mathematical analysis of atmospheric models with moisture, and I will discuss some of the joint work with different people, as I will mention the names of the collaborators when I get to the right transparencies. So I start from the very beginning, from the Rayleigh-Bénard convection or Boussinesq approximation, which is the first equation is the equation of conservation of momentum. U is the velocity field, which is unknown. P is the pressure, and T is the temperature. These are unknowns. This is the Coriolis force because we live in rotating Earth. And this is the incompressibility condition. So I'm talking about incompressible fluids now. However, there's a parallel program in the case of compressible flows, which is together with Xen Liu. I'm not going to talk about that today. And this is the heat transport. This is the heat transport equation, which is coupled. So the equation is forced by the temperature. And this is like in the atmosphere. The air is heated, and therefore by buoyancy it goes up, and therefore the cool air comes down. And this is the equations of motion. Now, this is equations that we interested in from partial differential equations point of view, and we'd like to talk about regularity or singularity for this equation. Now, it seems that understanding this equation is intimately related to understanding the Navier-Stokes equation, and this is the Navier-Stokes equation. And we don't know yet the global regularity of the Navier-Stokes equation. And the result that we have, there are many results about criteria for regularity for Navier-Stokes. I'm going to isolate one of them and mention this particular regularity criteria, namely if the velocity in the L6 norm to the power 4 is integrable in time, and therefore it's finite, then you have, if and only if you have regularity for the Navier-Stokes equation, and at the same time also for this equation, the Boussinesq equation, which is more intimately related to equations of motion in the atmosphere. Now, there's this particular criteria that I just mentioned. This particular criteria is one of a family of criteria which is called the Foyash-Lerjanskaya-Prodi-Serin conditions, which says strong solution in 3D Navier-Stokes exists if and only if the velocity field belongs to LP in time of LQ in space, when you have this relationship between P and Q. And the particular case when Q equal to 6 and P equals to 4 is a particular case of this particular criteria. Why I mentioned this criteria? Because it becomes clear later. So the Navier-Stokes equation are known to be in three-dimensional case to have global existence of weak solutions. And I'm talking about Leray-Hopf weak solutions, namely the ones satisfy energy inequality, short-time existence of strong solutions, and we have uniqueness of the strong solutions. And the open problems is the uniqueness of the Leray-Hopf weak solution, namely solution that satisfy energy inequality and global existence of strong solutions. And the last one is basically the millennium problem. Now, since I'm going to talk about the atmosphere and the oceanic dynamics, therefore we are on the Earth. So what happens is I'm looking at climate models or at models in which we're talking about larger scale oceanic circulation. So we have this kind of like horizontally large scale kind of movement that we would like usually to model. So these are the currents that people are interested in at the planetary scales. So taking this into account, so I go back into the very first equation, namely the Rayleigh-Bénard convection equation. This is the Boussinesq equation. And now let me write it decompose it into the horizontal component of the momentum. H stands for horizontal. And this is W is the vertical component of the velocity. And this is the incompressibility. And wherever you see nabla H means that we are in the horizontal direction. And the same thing for the equation for the temperature. And they are coupled, as I said, through the buoyancy term, which is basically this term T times G. G is the gravitational. So the velocity field here is the horizontal velocity VH and the vertical velocity. Now, in the ocean, for example, a typical horizontal distance is orders of thousands of kilometers. Typical velocity is 10 minus 1 meter per second. Typical depth in the oceans is the order of few kilometers. And the Coriolis parameter, which is one round, this is the typical like one round every 24 hours of the Earth. And the G is the gravitational of the Earth. And this is the typical density in the water of the water in the ocean. If I take this into account and I cook from that typical values for the vertical velocity, it's like 10 to the minus 4 meter per second, typical pressure 10 to the 7 Pascal, and typical time scale is 10 to the power 7. And I go into the vertical momentum equation. This is the equation, and I put the typical values from ocean dynamics or from the measurements in the ocean or the experimental or the situation in the ocean. We gave this is W over T here, and then we will have here U, W over L, etc., etc. And we plug the numbers, we get something of the order 10 minus 11, minus 11, minus 11, 10, and 10. And therefore, there are 12 orders of magnitude difference. And as a result, geophysicists have no problem of dropping the first three terms in this equation, and to say that the balance at the vertical momentum is basically by the last three terms, namely between the temperature, buoyancy, and the pressure. And this is called the hydrostatic balance, which is balancing the pressure gradient and the buoyancy. And as a result, in the oceanic and atmospheric situation, because of the thinness of the atmosphere and the thinness of the ocean in comparison to the planetary scales, we will have, we introduce, we will get the following equations, which is called the atmospheric, the primitive equations. So where basically I replace the vertical momentum by this particular equation, which is the hydrostatic balance. And these equations are called the primitive equations of large scale oceanic and atmospheric momentum. So they are like the Navier-Stokes equation, except that the vertical equation and the momentum are replaced by the hydrostatic balance. Now, these equations have been introduced by Richardson, 1922, for weather prediction. Jacques Williams, Roger Timam, and Xiuhong Wang, 1992, gave some asymptotic derivation of the equations and formal derivations. However, there were some attempts to justify these derivations in some weak sense, etc. And the most recent result is by Jin-Kai Lee and myself in 2017. We gave rigorous justification of the primitive equation, and we gave error estimates in which global in time, and I will talk about that in a later moment. So the results that I'm going to talk about now is the one with the Chongqing Cao, my former PhD student, which appeared in Annals, but in 2007. And basically it shows about global existence of weak solutions, and it also talks about global existence and uniqueness of strong solutions. So I said this is the equation, the primitive equation at planetary scales. So if we look for a different formulation, namely I look to the incompressibility and recover the velocity field, the W, the vertical velocity from the horizontal velocity, we notice that the vertical velocity, it is related to the horizontal velocity through a gradient. So there is a loss of derivative. And this is one of the technicalities or difficult technicalities in these particular equations. The pressure can come from the buoyancy by integrating the vertically. And then if you look for the average in the Z direction, this is called the barotropic mode. And the fluctuation or the difference called the baroclinic mode. And now the equations that we have, if you average vertically, you get this equation, which is called the barotropic mode equation. And this looks like the average, looks like the 2D Navier-Stokes equation, except that in the nonlinearity, there is some part of the V tilde inside this VH, because VH is VH bar plus VH tilde. So there is something like Reynolds stresses kind of like them. However, this is in principle like the 2D Navier-Stokes equation. And now this is the tilde equation, the fluctuation, which is now, this is depending on all the three variables, X, Y, Z, and on the time T. This equation is a little bit complicated. However, there is no pressure in it. There's no pressure term. And this is the situation. So the question, do we know an equation of transport type with diffusion, which doesn't have pressure? The typical or prototype equation is the viscous Burger's equation, which is given by this and has no pressure. And this equation has a global regularity in 2D and 3D because of the maximum principle, because the modulus of U satisfy an L infinity bound because it satisfies this relationship. And as a result, you have L infinity bound, which is automatically give you the L6 norm that I mentioned earlier as a criteria for regularity. And therefore, we don't have a problem with Burger's equation. And now if you come into our situation, what about our system? As I said, the pressure is the main term that we need to worry about in the Navier-Stokes equation. So what about in our system? The pressure appears here, but this is like a two-dimensional Navier-Stokes equation, okay? But then there is the V tilde inside here. However, the V tilde equation has no pressure, and as a result, one probably can treat it like Burger's equation. However, if you try to treat it like Burger's equation, try to get L infinity estimates, one is not successful. However, what one is able to show is that V tilde, the L6 norm is under control. And as a result, one can also from here go into the horizontal average and then show that the gradient under control, because as I said, it is like the 2D Navier-Stokes, but with terms coming from V tilde, which is now you establish L6. And therefore, from here, by the Sobel embedding, you get the L6 norm is bounded. And together this plus this, you show that the L6 norm is under control. And this is the criteria that we needed to show the regularity. And this is the idea behind what's happening here. Now, there are some other results in this direction. I mean, by many people. As I said, the mathematical analysis started by the pioneer work of Leon Stimam and Wang in 1992. And then there's some other work by Breschet et al. And then there is some work by other people about start weakening the initial conditions in which to show existence and uniqueness. I would like to emphasize this result about local existence by Gonzalez, Masmoudi, and Rodriguez. And the result that I mentioned is the one with the Tsao and myself. And then there's other results by Hibe and Kishibara about the LP theory using the maximal regularity and the semi-group approach. Now, I would like to talk now about the mathematical justification of the hydrostatic approximation. So to talk about that, let me look at the Navier-Stokes equation. Forget about the temperature for a second. And I rescale the equation with the thickness of the atmosphere in comparison to the aspect ratio, in comparison to the planetary scales. And therefore, when you do this formal expansion, you get an epsilon, which is like the thickness or the aspect ratio. And therefore, you formally have this particular term that when you put epsilon equal to 0, you get this limit. And this is the equation, which is the primitive equation. The question, can we justify rigorously relationship between this and this as epsilon goes to 0? And now that we know that the primitive equation has a global existence, so probably you can relate the epsilon equation or the scaled Navier-Stokes to this equation, namely to the primitive equation. And here is the result that we have with the Jean Kiley. So first is a weaker result, like if the initial data is in the space H1, satisfying this kind of technical condition, one can show that the scaled Navier-Stokes V epsilon and epsilon W epsilon converges to V and 0 and L infinity, 0 infinity time in L2, and that the gradient converges to the gradient of the primitive equation. And therefore, we can show that the order of convergence in this case of order epsilon. And this is uniformly in time. And this is the first result. The second result, when you talk about stronger initial data, not in H1, but in H2, then one can show similar results that this is converging here L infinity in H1, and that the gradient is converging into this equation in L infinity in H1, and W epsilon converging to W in this particular norm, but the convergence rate is order under epsilon. It's important to emphasize here that the scaled Navier-Stokes equation, we know that it has, because the initial data is smooth, we know that this, or well-prepared initial data, we know that the solution is only for short time. We have local strong solution. However, after that, you don't have, we don't have uniqueness. However, in this particular case, one can show for this particular case, when epsilon is small enough that you have global existence of the scaled Navier-Stokes equation, and therefore this result is valid. Now, what happens if you have no viscosity? All this relying on viscosity and connecting the viscous primitive equations to the Navier-Stokes equation. Now, what happens if there is no viscosity? So in the case of there is no viscosity, when you look for the implicit primitive equation, the first equation we looked at is the result with the Tsao, Ibrahim, and Nakanishi. And there is a similar result around the same time, basically with Wong. And the result is we look at the primitive equations. These are the primitive equations, and without viscosity and without the Coriolis force. And what we were able to show that in this particular case, when I look at it in a strip, namely I look for this in omega in the domain, which is a strip, xy is periodic in xy, and in z is like between 0 and h, and w is equal to 0 up and down, one can show that this particular system of equation has a singularity, form a singularity in finite time. I don't want to get into the details about the proof of this result. However, I would like to mention that this result is also called sometimes the hydrostatic Euler equation, because it is like Euler equation, but then replaced by the hydrostatic term, namely, especially when the temperature equal to 0. And as I said, this result is without rotation. However, recently there is a result by my student, Chui-Wan Lin, in which he can show that even if you add the Coriolis force, one can show there exists an initial data for which you have singularity in finite time, even with rotation. However, the initial data depends on the rotation. And now the question becomes, for those who are familiar with the results of Babin, Mahalov, and Nikolayenko, and Chemin, and Gallagher, and Grenier, and group, in which one can show that the lifespan of the solution of Euler equation with rotation is prolonged as long as the rotation is increasing. And now the question becoming, well, here you have initial data depends on the rotation, therefore you have singularity. Now, if you take initial data independent of the rotation, say of order 1, and let the rotation go to infinity, do we have a global regularity? And this is a result which is on the making, and it's going to be being written with Slim Ibrahim and with Chui-Wan Lin. Now, let me move into the next topic, where I would like to talk about situation with moisture. So in the lower troposphere, the wind velocity is opposite in sign, and therefore can be sort of approximated by cosine z. And this is in some sense like the first Fourier mode in the z direction. And then if one really take the primitive equations and really project into only this mode, forgetting about the other modes. So then because of this, one can look into the solution to be like the barotropic mode. And this is the only part of the baroclinic mode. This is at the level of modeling, okay? So accordingly, the W and the temperature equation will satisfy this relationship. Here, phi is the pressure. We change the notation because we're following the notation of the people who basically people who are doing the modeling. And as a result, okay, so performing the Galerkin projection only on one mode in the baroclinic direction, Freyson, Maida, and Paul Louis introduced the following model from the primitive equation, in which U is the barotropic mode, namely function of xy, and V is the coefficient of cosine z, which is the baroclinic mode. And now this is the temperature. However, the temperature is connected through a source, and this source of the temperature is theta that needs to basically be figured out through a coupling to the moisture. And now this equation, if you think about this equation, if you look at this equation, forget about the theta equation. Suppose theta equals to 0. This equation, I put here the plus sign with the red color, because this looks like the magnetohydrodynamic equation, the two-dimensional magnetohydrodynamic equation, okay? But then the sign should be with minus, not with the plus in the magnetohydrodynamics equation. So therefore, this system looks like the magnetohydrodynamic equation, but in the magnetohydrodynamics equation, the divergence of V initially is 0, and because of the minus sign here in the magnetohydrodynamics equation, then the divergence of V remains 0 all the time, and this allows us to show global regularity for 2D viscous magnetohydrodynamic equation. However, here the situation is different. We cannot, even if divergence of V initially is 0, we cannot guarantee that it remains 0, and therefore the situation is a little bit more complicated in this particular situation. So for this particular equation, as I said, the question is, what about the source for the temperature? So again, following Frierson, Maida, and Paul Wee. So if you look into a Q to be P is the precipitation, and Q is something to do with the moisture. It is really transported, but then there is another term coming from the divergence of V, which is not zero, and P is the capital P is the precipitation, and you can see that there is a parameter 1 over epsilon here, which is a very small parameter, which is convective adjustment time scale parameter, and epsilon very, very, very small, which is basically tells you that when you get into saturation, that's why the plus sign, as long as you're negative, you don't see the P, but the minute you are exceeding some threshold, then there is there is rain, and therefore there is a source of moisture which is coming from this particular case. And therefore, this is an equation which has a singular perturbation parameter epsilon, which is very small, and there's this plus sign which makes the nonlinear, this equation nonlinear. So if you look at the putting things together, we look at specific model, which is by Frierson, Maida, and Paul Wee. This is the equation as before, but now we replaced the Q equation. This is the temperature equation, and this is the precipitation or the moisture equation. Now the question, we would like to look for the global regularity of this system when epsilon is strictly positive. And the next thing is when epsilon is very small, computing with this is very complicated because you have epsilon very small, and therefore you need to take delta T extremely small, which makes it computationally prohibitive and very expensive. And then the next question would happen, okay, what happens as epsilon goes to zero? Can we recover a system of equations which is independent of epsilon such that the solution of this system remains close to the limit equation? So this is singular perturbation kind of like problem. So the question, what happens with this model as epsilon positive? What happens to the limit as epsilon goes to zero? And then what happens is the relationship between the solutions of this model and the epsilon, vanishing epsilon model. So what happens in this case, if you look at the relaxation limit when epsilon goes to zero, formally you get all this equation. However, because here you have this plus sign here, if you multiply by epsilon, then this quantity should always remain negative. Therefore, this quantity here must be negative all the time. And as a result, when you go into the limit equation, you don't get equation, you get an inequality, less or equal to zero. And then we need also Q to be less or equal, E to be less than equal to zero. And then when Q is strictly less than zero, we get the system. So the limit situation or the formal limit situation is not a system of differential equation, but a coupled differential equation with differential inequalities. So investigating this particular system, especially the uniqueness part, is not straightforward, because if you want to show the uniqueness, if you take two solutions, you look to the difference between them, this inequality, basically we are in trouble, because if it is less or equal, then the difference, you don't know what's happening with the difference. The difference will not be having the same sign. So nonetheless, the result that we have in this particular thing, in this particular situation, let me recall what's happening with this particular model. So global regularity and justification of the relaxation limit of the linearized version of this model in the inviscid model, it has been done by Maida and Souganidis. Now the global positiveness and justification of the nonlinear relaxation limit has been done with Jin-Kai Lee, and we even show that the error or the difference between the epsilon model and the limit model converges with the rate of square root of epsilon, where epsilon is the relaxation limit parameter. So we have the global existence and uniqueness of both systems, and we can show that one system is converging to the other, and we have explicit error. But we need viscosity, and the word of Maida and Souganidis was about the linearized version in the inviscid case. So now I will go back into warm clouds. By warm clouds, we know that in the clouds, it is the thermodynamics is very complicated, and I don't mean in this for this audience to talk about complicated thermodynamics and microphysics, because in the clouds, the water can find itself in all the three states: solid as an ice or snow, it can be vapor, or it can be water, like in rain. And therefore, the thermodynamics is very complicated. And I'm going to talk about a model which is called warm clouds, in which that the water in the clouds can find itself in only two forms, namely either liquid or vapor, but not ice. That's why it's called warm clouds. So if I call QJ is the mixed ratio, V is for vapor, for rain, and for and cloud water. So QH is in comparison to the density of the dry air. Rho D is for dry air. This is the situation where, I mean, this is basically the graph in which you have the exchange of vapor, water from vapor into rainwater, into cloud water. There's a collection of falling rain, there is auto conversion, and so on and so forth. This is the diagram of the exchange of the concentration or the mixed ratio of the water in the clouds. So the saturation mixing QVS satisfies the following situation. So if I denote by SE, these are sources of the different kind of like water in the clouds. And as I said, these are the QV is the vapor mixing ratio, and QR is the rain mixing ratio, and QC is the water mixing ratio. These are the quantities which is the sources. And now these different quantities, QR, QV, and QC, satisfy an advection equation. ddt of QV is given by df dt is given by this advection equation, by the vector field, with sources. And the sources, as I said, they are from the previous transparency here. And again, you can see that there is this plus sign, namely, there is something happening that below saturation, nothing's happening. But when you exceed certain threshold, then some action is taking place. And this makes the equation much more complicated and much more nonlinear because of this cutoff heavy side kind of like function. This D operator, DQV and DQC, etc., these are diffusion operators. dF is given in general by the Laplacian, plus in the vertical direction, you have this kind of like non-homogeneous sort of diffusion part, but altogether it's an elliptic operator. So now this is the model that we would like to investigate and study, where the S are nonlinear functions of the QV, QC, and QR. And T is the temperature, which is basically coming from this cycle of thermodynamics of interaction of the different mixed ratios of the water in the clouds. Now, the first situation is we assuming that the velocity field UV and omega, and by the way, here it's omega, not W, because we're following the tradition that in the atmospheric sciences, that's how they call the vertical velocity, they call it omega. So it's not the vorticity as commonly in the fluid mechanics community. So I'm assuming that the equation U, or the quantity U, V, and omega are given to me and they are smooth. I will specify that in a moment. And I would like to look at this kind of like sort of reaction diffusion kind of things. Diffusion because of the D operator, and it is transport because of this operator, and reaction because, as I said, the S part are in some sense like kinetic, but then there is the plus signs, which is you need to look at that. So what do we have in this case for a given velocity? So the result, of course, we have to do it in specific domain with certain boundary conditions, which I don't want to be too specific about at this moment. I don't want to be too technical. So the result that we have is the following result with the Sabine Hetmeyer and the Rupert Klein and Jin Kai Lee, which appeared nonlinearity. It says the following: suppose the initial data for the temperature and the mixed ratios is in L infinity H1, be non-negative originally, and for given velocity field, and the velocity field is specifically given and it is smooth, enjoying this regularity, and it is incompressible, and satisfy the right boundary condition, there exists a unique global solution for this particular system that I mentioned to you earlier, but for a given velocity. And now the question is the uniqueness part, what's happening in the uniqueness part, which is one of the issues here, namely that you have the plus here to the power beta. Notice that you have here power beta, which is a fraction, especially when beta less than 1. Even at ODE, when the nonlinearity is fractional power, like y dot equals square root of y, and y at 0 equals to 0, we know that the nonlinearity, if it's not really Lipschitz holder, this is the prototype for the case we can show non-uniqueness. So how come we have uniqueness in this particular situation? So it happens that the nonlinearity in this case is cooperative in the sense that it enjoys after you make some change of variables. So instead of doing with the original system, we make some change of variables. So I call Q to be QV plus QR, etc., etc. We then get an equation in which we have a quantity which is of this right. Instead of this quantity, we look for a quantity of QR, and the SEV appears only in the QR equation. And now we rely on the fact that QR to the power beta is a monotonic function. So QR1 minus Q of R2, when I take the inner product trying to do some kind of energy estimate, it is non-negative, therefore can be dropped. And that's how we show the uniqueness in this particular case. Again, I don't want to get into too technical. I just basically emphasizing what are the technicalities, what are the technical issues, and how do we basically overcome them. So the technical issue that the nonlinearity is a fractional power and fractional less than 1, where basically the ODE theory usually does not guarantee uniqueness. On the other hand, with the right change of variables, one can show, or one can take advantage of the fact that this nonlinearity is some kind of like one-sided Lipschitz, what's so called sometimes, in which it basically gives you the uniqueness as needed. So now, as I said, so if we assume that the initial data is in the space H1, and the initial temperature and mixed ratios of the water in the cloud is in L infinity, then the coupled microphysics dynamic system with the primitive equation has a unique global time solution, and it satisfies that if initially you are positive, then you remain positive, because this has to make sense physically, these quantities, and the solution is unique in this particular case. Now, I am getting, so this is, I would like to, okay, so this is in the case of coupling to the primitive equation, because I will mention something here. As I said, the previous result here is, I will go here back. The previous result here is we are given the velocity field. So we are given the velocity field, and then we look for the reaction diffusion type system. This is the system with the nonlinearities like that, and we show global existence and uniqueness. Now, suppose I would like to look into the coupled system with the primitive equation, namely, the velocity field is not given, okay? So, namely, I have a velocity field which is governed by the primitive equations that I mentioned to you earlier in this talk, and in which we showed that when it's coupled to the temperature alone, you have global existence and uniqueness. Now, the temperature is not really just have mind of its own, it is coupled to the microphysics of the moisture, namely into this system of equation that I just mentioned to you here. This system of equations. Oops, sorry. So the temperature is coupled with the moisture through this, and the temperature is the buoyancy for the velocity field. So now I look at this system of equation with the SEV, SCD, SAT all given previously, coupled with the velocity field, which is governed by the primitive equation. So now also for this system, we can show global existence and uniqueness. And how do we do that? It is done in principle by iterative procedure. Namely, you give me the velocity field and then I solve for these equations and for the temperature. Then I take this specific temperature and go and solve for the primitive equations with the initial value with the temperature that I solved from here. And then after I do that, I have a global existence for the primitive equations. Now I take this new velocity from the primitive equation, I come back into this system with the new velocity, updated velocity, and solve and show existence and uniqueness. And then I get a new temperature, then I go back and couple it to the primitive equation, and I keep iterating this procedure. And the idea is to show that this process has a fixed point, namely, given velocity, solve for the moisture, get a solution, and then from that you go back into the primitive equations and find the new velocity, and then update this new velocity, find the moisture, and you keep iterating and showing that this system has a sort of a fixed point. And this is the idea that we have into this new result with the, also with the, sorry, also this with, oops, something wrong. This new result with Hittmeyer, Klein, Lee, and in which we show that for a given initial data for the velocity in H1 and temperature is in H1, and this is the mixed ratio of the moisture, and if they are initially in L infinity and they are non-negative, then the coupled microphysics dynamical system with the primitive equation has unique global in-time solution, satisfying that the relevant quantities physically they are non-negative, and this is physically supposed to be, because it has to be non-negative because they are concentrations or they are mixed ratios, and the temperature satisfying this regularity and the velocity satisfy this regularity. Now I would like to mention that there are some other results by Kotizilati, Huang, Kukavica, Timam, and Zayan 2015 about primitive equation with moisture, but different kind of like microphysics of moisture than the one that I mentioned in this particular case. I think it is now 40 minutes, and I'm about finished with my lecture. Before I close, I would like to tell you where we are standing now. What is next? The first thing is that in parallel, now we're having similar program going on with Xen Liu and with Rupert Klein and with the Sabine Hetmeyer, in which we are doing the case of the primitive equations, but compressible, because compressible primitive equations seems to be more realistic in the atmosphere. And we have parallel program going in there, and in particular trying to justify all kind of results in this particular case, especially the derivation of the primitive equations from the Navier-Stokes equations, and then coupling it to the moisture. And the second project in parallel that's going on is what I mentioned earlier, is with the Slim Ibrahim and the Shuan Lin, in which to show that in the inviscid case of the primitive equation, does the rotation prolong the lifespan of the solution? Namely, if you give me initial data of order 1 of the inviscid primitive equation with rotation, and you take rotation large enough, can you make the lifespan of the solution longer and longer? This is, in some sense, in the spirit of the result of Babi Mahalov and Nikolayenko and Shima and company, and Gallagher and Grenier. However, it is, in the case of Euler, it is unknown if there is a singularity, at least in the periodic boundary condition case, even though now we have some new result of Tariq el-Gilbi and of Masmoudi and the Goul, in which there is particular situations where there is some singularities of the axisymmetric Euler, but we don't know in general that there is, for smooth initial data, singularity for Euler, and therefore using the rotation for prolonging the solution, is this a matter of just technicalities, or is this really a need for the rotation to do that? However, in the case of the primitive equations, we know that singularity is developing in finite time, and therefore the question remains valid: does the rotation really prolong or prevent the singularity from happening within short time? And I would like to thank you and thank the organizer for giving me this opportunity. and I wish you all to stay safe. Thank you very much.